the second part of the procedure and feed of ocean plan. Feed is for front-end engineering design. So I will speak about concurrent engineering and design change management, and SCM is for supply chain management. But first, little of motivation why you should listen to me now is because ocean plants are really complex. We already talked about it many times. A lot of the components are interdependent, meaning, for example, if you plan to have a oil tank and suddenly you want it to be bigger, then you have to rethink about maybe the size of the pipe, maybe the steel structure maybe should be also stronger, for example. So a lot of components are interdependent, and that makes a complex design. Also, the ocean plant have to work independently in really hard conditions with a lot of wind and waves, and also the security is big. It's really important for ocean plant. For all of the reasons, good management is crucial for a nice ocean plant. And to illustrate this, I have a video that shows what can happen on an ocean plant if something gets wrong. And so it happened in the North Sea.
My team and I always had.
In the North Sea, next to United Kingdom, in 1988.
July 6, 1988. 120 miles northeast of Scotland. The Piper Alpha oil rig. At 14,000 tons and 2.5 times the height of the Statue of Liberty, it is one of the largest rigs in the world.
Piper Alpha was the world's most successful oil rig. What that means was that in a single day, Piper Alpha produced more barrels of oil than any other oil rig or oil platform in the world.
A crew of 226 rotate shifts to keep the oil and gas flowing.
Okay, I will skip a part and you will see what happened. Suddenly,
a spark suddenly ignites the escaping gas, and an explosion rips through the rig. Confronted by 700-degree flames, most of the 226-strong crew are now either dead or severely injured.
The nearest analogy is the cross between the Titanic and the Towering Inferno.
All hell was breaking loose on that thing. It was just a scene for hell. So the way they described it, a scene of absolute carnage and hell. Flames, explosions, debris. Things were escalating so fast at that point that it was almost impossible to take things in.
By 10 to midnight, less than 2 hours after the initial blast, the Piper Alpha is on the verge of collapse. Finally, the rig's legs start to give way, and the Piper Alpha starts to slide into the sea.
Where A module was, and the rest of the platform just started drifting apart. The 3/4 of the platform just very slowly fell into the North Sea. That's my worst memory of the night. It's I know for people who were still on it, it would have gone at the bottom of the sea.
A total of 167 men lost their lives that night. Just 61 survived.
not really funny, but just to show you how important it is to have a properly project, like well executed.
Click on arrow. Click it down. Put the arrow.
So design process. Really often the input is given by the client there that give design basis to the engineer. The design basis of the functional requirements there. For example, where should the ocean plant be? What kind of, is it oil or gas that it should extract? Which amount of them? Also the price. Yeah. And also some specification. Specification are kind of requirement, but more details. So, and then they give it to the engineering. This is because it's the input, and the output is the design. And the engineering propose a design to the constructor and to the procurement part. So to purchase the equipment, for example. And yet the engineering part has contact with the client. So they give the document to the client, and the client says, okay, I'm happy, I'm not happy, and adds a comment or something. And also to the vendors, so there is always communication between the parts. And here we can also see the engineering part, the procurement part, and the construction part. Okay. This is really similar, just the procurement part is here. Yeah, construction part and the clients variable is the same. Okay, now concurrent engineering. So first we have the sequential engineering, which is this one. So the engineering part propose a design, and then when the design is fixed, they give it to the procurement part that buy the equipment and something. And when we have the equipment, you can construct the plant. That was before. Here is a new methodology, which is the concurrent execution. And you can see the engineering part finished, but before it finished, the procurement part already started, and the same for the construction part. So now maybe I can ask you, what do you think is the advantage of this methodology instead of this, or maybe some disadvantage? Do you have any ideas?
It takes less time.
Okay, yeah, right. Time is really important. This is faster, and you know that time is money, and time is also like really important to be competitive in the market for an engineering company. Yeah, other ideas? Maybe some disadvantage of this methodology?
If something goes wrong at a certain point, you already bought the pieces, so
yeah,
go back.
Exactly. If you notice, oh, maybe we should have done this differently, then it will have more cost and it's more complex to have change in this system than in this system. Yeah. Other ideas?
Better communication between department of company.
Yeah, that's true. Here, this require a lot of communication, and how to say, it's much more complex, so you need to communicate much more. Okay, and this methodology we can compare it to the parallel processing in computer science. Like they use multiple, I don't know how exactly it works, but the computer to compute the same thing parallel and not sequential. So again, this is the sequential execution. The engineering gives some drawing to the constructor and a bill of material to the procurement, and the construction part need the material to begin to build. And in the concurrent execution, you have like more steps, so you don't have only one bill of material, but many, and also many drawings, so you can work like parallel. And this, we already talked about it a bit. This gives more challenge. So you have to get the design input early. Also, should avoid changes in your design. Also, integrate the EP and C work process for engineering, procurement, and construction. Okay. So get the design input early was the first complication here, the first challenge. And usually it's how it works. So we start with the process simulation. So this is done mainly by the chemical engineers. So simulate the process, and then they say, okay, maybe we need like a pump and a boiler, and yeah, something like this. A compressor, for example. So they make a list, and they give the list to the vendors, and the vendors say, okay, we can give you maybe this design of compressor, this design of boiler, so, and then you end up with the foundation drawing. Okay. And also, engineering must be right first time, which requires experience, good coordination, discipline, and anticipation. Here you have an example where I guess something is ill-dimensioned, like there is a problem in some pipe here. So what does it mean? It means we misestimate this part. So then we have to rethink about maybe the layout. Maybe we need more space to have bigger pipes. And also, it also means we have to maybe rethink about the steel structure. So if you get it right the first time, it's great. And also, yeah, this means the simulation can be really helpful in this case. You can see what kind of thing can happen in a better way. And also you should avoid changes. Yeah, the changes can happen because of technical issues or some reviews or maybe some new requirements from the client. And then you have to choose, is this change avoidable or not avoidable? If you can avoid this change, then do it, because the impact of the changes is exponential with the time. So the earlier you change it, the better it became. And if you change something late, then you have to rethink about the whole process, and that has a lot of costs. Also, you have some system to identify the impact of the changes. Again, the simulation can help in this case. Okay, so control your supplier and subcontractor. I already said that in ocean plant, many elements are interdependent. So if one element depends on many others around him. So if your supplier don't give you one element, then your whole system has to wait, and this costs a lot. So timing is really important. And also the quality is important because if one element breaks, then all the element that depends on it cannot work. So control your supplier, you get what you inspect, not what you expect. And also if you know your supplier, it's better. Yeah. Okay, project organization. On the top of it, we have the project manager, and here you find the three main parts of engineering part, procurement part, construction part, and here is also control for the project. In the engineering part, you have the project engineers, but also some more specific engineers like process or instrumentation or electrical. For the procurement, you have the purchaser, the expeditor, and inspector. And construction, I think, is pretty straightforward. And the control inspect the contract, schedule, and cost. Here is the process design, and it's a bit complicated, but we start here with the process flow diagram. It is given by the chemical engineering most of the time, and yeah, so they design, they show which process you have to use, also do the material and heat balance. And after this, we get like a list of equipment we need to process the ocean plant. After this, we can also do this, the pipe and instrumentation design, and this allows you to do a list of the pipe and instrumentation. And on the two next slides, I wrote like some details about this process design. I won't go through it in details, but if you're interested, you can read. So here is pretty much the same. You have the process flow diagram here with the heat and mass balance, and this gives you then the equipment specification. For example, pressure vessels, heat exchanger, many things, and you have to purchase them. So the procurement part, then try to buy it, and then you can do the layout and also more detailed stuff like the electric part, and also the PNID, so pipe and instrumentation, give you pipe and instrumentation. So this one looks a bit complicated, but we already spoke about most of them. Maybe procedure of topside engineering. Topside means the part where the process, where they process the oil or something. It means above the ocean and above on the planet, so top. That's why topside. So you begin with the design basis, and then use some simulation to see the process. This gives you the PFD, the process flow diagram. And after this, you can use the pipe and instrumentation diagram. And after, you can be more specific. For example, the safety, control chain. You get the equipment list. Then you can have like your whole project. Okay. So that was all from my side. Thank you. Question?
Question.